All right, let's get started, everyone. I'm gonna jam through these last slides, and then we will get started with actually learning how to collect data because that's what I want the focus of the workshop to be. So, okay. So yesterday we talked about eye blinks. I changed the background so I remembered that I went through these already. Sorry for the high contrast. Um, so we talked about eye blinks, how they're very common, and ways that we can get rid of them, both through artifact detection and rejection, and also some correction methods. And we also talked about how we can just design our experiments and tell our subjects things in order to make eye blinks less of a problem. But there's lots of other artifacts. Another massive class of them are muscle artifacts, and we're mostly getting these from our neck and our facial muscles, which are quite large and are very close to our sensors that we're recording from. And these also have a set of things you can do to make things better or remove or detect. So just to give an example of what these look like in EEG data, this is some raw EEG data. It's been high pass filtered so that we can essentially keep it all on a straight line. I'll explain why that happens when we do analysis. But here are 64 channels of EEG data, and this is a pretty clean section of data. We're seeing eye blinks. You can see these nice little bumps, or what look like blinks. This might even be something related to heart and not blinks. I don't know. But we're not seeing a lot of muscle artifacts, and I can tell because when you see muscle artifacts, you see these massive high frequency spikes. So these are usually very apparent. Sometimes it can be much larger than this. This was during an actual experiment, so when the subject is taking a break, they're not really moving around that much. But before you start recording data and you just look at activity from people, it's all over the place and it's crazy. So again, the reason why it's so large is we're recording EEG data at the scale of roughly microvolts, and muscle activity is easily in the millivolts range to hundreds of millivolts. So it's significantly more powerful than our underlying neuronal activity that we're recording. Muscle artifacts are mostly caused by the fact that the most common ones are around the temples. There's these giant muscles, the temporalis muscles, and if you look at the activity of electrodes that are directly on this region, they're essentially always noisy. So even if you have really, really good recording quality, you're the best EEG researcher in the world, and you can cap people perfectly, you'll still often find that, especially in these regions right here with electrode locations T7 and T8, they're just almost always noisy. And that's because these muscles are gigantic. Recently, I don't know, a couple months ago, I was recording a subject with a professor, Andrea Chiba, and we just had one of her research assistants in the room. Hey, Shauna. And we weren't really paying attention to the subject's condition, but we noticed that like all of the electrodes on her, I think it was her left side, so like T7 and the electrodes around there, were bursting with a lot of high frequency noise, but her right side electrodes were totally fine. And after we were more careful and observant human beings, we noticed that she actually had a broken arm, and her arm was like in a sling, and so she had all of this tension in her muscles going all the way up her body, and you could actually see that like those muscles firing off. It was kind of crazy. So detecting muscle artifacts is pretty simple. I mean, obviously you can see them just with your eye, and again, these aren't even that bad. And in general, we can just check for higher frequency noise. Most artifacts are typically much faster than 30 hertz. And we can also look for high power, especially in the 100 hertz range. It's usually going to be muscle activity. Because again, the EEG activity in those much faster frequency ranges is quite attenuated. We don't really see a lot of it. Muscle artifacts occur a lot during rests when participants are instructed that they're allowed to move around. And this is why it's important to actually give your participant instructions, because if you just let them do whatever they want, some subjects will like tap their legs or move their feet, and some people will chew or just like rotate their head. They'll do all sorts of weird stuff, which is why instruction is very important. And again, what I was talking about with the temporalis muscles, some electrodes are just more likely to record more and higher muscle activity. These can be seen with visual inspection. They'll usually be higher frequencies. And again, you can typically, most of the time, so with like T7 and T8, sometimes there's just nothing you can do. They will always record high muscle activity. You just really want to get the impedances of your electrodes as low as possible so that you're getting high quality data either way, but it's sometimes they're not salvageable. But what can you do to correct for muscle artifacts? None of these are perfect, just like with eye blinks. Low pass filtering is an option, so if most of your muscle activity is in the higher frequency ranges, you could apply, like a filter with a cutoff of 15 hertz or something if it's appropriate, and that could get rid of some of your muscle activity. Of course, it's not going to get rid of all of it, and it's possible that that underlying activity has corrupted the data in ways that's not visible, visually, but has altered the state of the signal. You can also drop high muscle activity channels like T7 or T8. Again, it depends on what you're doing. Some studies, you're really only ever looking at a single electrode, so if T7 and T8 are noisy, but like everything else is clean, it's not really the end of the world. And this is sort of a limited technique, but you can re-reference. So if mastoid references are picking up your artifacts like from your neck or from heart rate, then you can try to use a common average reference, or use a reference electrodes that are slightly higher, like TP9 and TP10. But it really depends on the experiment you're running and which ERPs you're trying to elicit, if that's going to be appropriate or not. So none of these are sort of catch-alls. It's sort of a toolbox, and you have to assess which are appropriate to use in which scenarios. But the best thing, which is going to be a theme in all of these, we want to follow Hansen's axiom and try to design our experiments and instruct our subjects such that we don't elicit these artifacts in the first place. So you want to have participants seated in comfortable chairs. That's not really going to be possible for us today. These are okay, right? I mean, they're not too bad. But a lot of experimenter chairs and real EEG labs can be these nice, comfy couches. You don't want them to be too comfy because then subjects will fall asleep, or just get drowsy, which is not good. You also want people to sit up straight, because if you're like slouching like this, you might be generating additional strain on your neck muscles. And you also want to just show participants these artifacts. This is incredibly useful because even kids, there's a classic example where, I'll have a subject sitting there with their cap, and I'll just have them relax, and the traces will get nice and clean, and then I'll have them clench their jaws, and you guys are all going to do this, and it just completely destroys the data. And once you see that, once you're bridging that connection between what you're recording and what the subject is doing, people tend to like piece it together, like, okay, like this is very obviously ruined. You don't have to be an expert to see that those signals have distorted everything. Okay, now ocular artifacts. So this is not necessarily exclusive to blinks. This can be the ocular artifacts due to moving the eyes. This can affect many electrodes, but it's gonna be most prominent on the frontal electrodes. And you can detect this with EOG. Rejecting is easy, same with eye blinks, but correction can be difficult, and some of these artifacts can be impossible. Yeah.
Is this like another type of like muscle artifact?
Not exclusively. So that's a really good question. So although some of the muscles that are involved with, blinking or sort of focusing the eye, especially if you're like trying to like narrow in on your sight and squint a little bit. Obviously, those muscles will have some impacts, but uh, the big source of all of these artifacts is what we were talking about yesterday, which is the dipoles of the eye. So because the eye is a dipole, whenever it's moving, laterally or up and down, it's essentially the electric field of the eye is changing, and those fields are very easy to record with EOG or with EEG. But there is some muscle activity that will also be picked up, but I don't think it's not the most common source of noise. But again, like if you're squinting or something, you'll be able to pick that up. Good question. So different ocular artifacts. So this is an example. We're looking at FZ, which is an electrode right here, pretty frontal, but not directly on the scalp or anything. We're looking at our HEOG, which stands for horizontal EOGs, which is electrooculogram. And these are going to be the electrodes that are on the sides of the eyes. So this will be your HEOG. Whenever you're moving, and actually, I don't know why, I think these are all different examples of HEOG things. rather than being at the same thing, because you don't usually record multiple, like you wouldn't record 3 sets of HEOGs. But the thing to keep in mind here is this stereotypical type of pattern, which is this step-like function. So whenever somebody moves like if you're looking straight ahead and you move your eyes to the left or to the right, it's going to generate this massive spike that is sort of like a step, and it's going to level out there. And then when you move your eyes back, it's going to go back to the original DC offset that your signals were at. As you can imagine, this artifact is pretty easy to detect with EOG electrodes, but it can be somewhat difficult if you don't have dedicated channels. So there is a known formula for sort of how these signals degrade as you get further away from the scalp. So it's like, I can't remember what the exact ratio is, but as you record further and further away from the eyes, the signal sort of drops off linearly. So you theoretically can pick it up, but it's not as reliable. And if you're doing things that require heavy eye involvement or the lack thereof, such as what we were talking about yesterday, the N2PC task, that task is very dependent on the subject not moving their eyes. So if you are trying to collect good data, you absolutely need a method to be able to determine which trials somebody moved their eyes, so you can drop those trials. But this can also be useful for detecting microsaccades and larger saccades and all that stuff. So how do we correct for these? This is an important quote. This is from Steve Luck's book. Procedures that attempt to correct for the EOG voltages produced by eye movements cannot correct for these saccade-induced ERP responses. So what this means is that although we can account for the artifacts generated, or maybe we can account for the artifacts generated by the fact that the eye is a dipole, for example, we can model that and we can try to regress it out of our data or use ICA to remove it from our data. There's still this phenomenon that's happening perceptually, which is your eye is going to move to something. It's going to, see a stimulus on the screen or maybe the lack thereof. And that saccade, this sort of fixation locked event, is going to be generating some sort of cognitive phenomena that are going to be affecting the state of your brain. If there's a way to fix these artifacts reliably, that method is unknown to me. It seems like a nearly impossible to just like straight up impossible thing to correct for. But depending on your experiment, it may or may not matter that much. It kind of depends. So like you can imagine that it maybe is more important on a visual search task than like an oddball task or something that is really looking at visual perceptive activity versus probing for more like simple cognitive phenomena. I don't know. But either way, this is important to note that although you can fix some of these artifacts, there are sort of these propagating side effects of artifacts that are just not repairable, at least not now. So again, you can correct for EOG signals with regression after you detect the step. You can use the Gratton method for this. You can also find slower eye movement with video eye trackers, but correcting for this would be difficult. So although you could identify that the eyes are moving using non-electrophysiological tools, you're pretty much limited to just rejecting those trials and not correcting them. Again, not possible to correct the ERPs you get from the eye movements, but it is possible to correct for the eye movement activity. And what can we do Hansen's axiom style? We can show participants these eye movements and we can instruct them that they need to fixate on the center of the screen. So almost all experiments that we run will have a fixation cross or a dot in the center of the screen, and participants are instructed to sort of keep their fixation on that. And when we're recording EOGs, which we're not going to be doing today or in this workshop, you usually will have subjects move their eyes up and down and left and right, and you can show them like, hey, again, this is distorting that signal. But that's pretty much it. And again, otherwise, if your study depends on non-movements like N2PC, then you definitely need to acquire EOG. There's not really an alternative. And the last set of artifacts we'll talk about today are just environmental noises and skin potential. The most common is 50 or 60 hertz line noise, depending on which country you're in, and also slow sweat noise. So this, as your skin sweats, it changes potential, and these like create these very, very slow oscillatory artifacts. And you can often remove these with simple filtering techniques, so you don't need special artifact projection tools, although certain tools like ICA can help. So line noise is the most common thing. We're going to get line noise just from the environment, from our lights being on if we're not in a shielded room. You'll also get it from monitors. It's funny, CRTs, the cathode ray tube monitors, are like dinosaur monitors for those of you who had never used them as a kid. It's funny, whenever I get subjects like undergrads into the lab, they're always like, "Whoa, crazy monitor." I'm like, "That's the crazy part, not the EEG setup or whatever." But anyway, those monitors can be incredibly noisy. I mean, it really depends. Some of them are okay, but if you get something that's detecting EM radiation and you put it next to those, they usually go crazy. Computers can also be a problem. Laptops that are not plugged in, laptops that are plugged in can sometimes be a problem depending on where your AC to DC converter is. So they're all over the place. It can be filtered out. Again, this has a very known characteristic. It's either going to be at 60 hertz or 50 hertz. For us, it's going to be 60 hertz, and you can just use a notch filter for this. So you can use a notch filter of like 55 to 65 just to be extra sure that you're going to get rid of the bulk of the noise. You can mitigate this by using DC battery devices. So, for example, rather than having these lights on, which again, we're going to be having them on, you can have battery powered lights that are just working off of double A's or something, and those aren't going to be inducing a 60 hertz noise because it's just DC power. You can also, when most of our amplifiers that we use are powered by DC batteries, so they're not plugged into mains. So the Cytons that we'll be using have little lithium battery packs, but in the lab, unless you have more old school systems that are sort of converting that signal for you, they tend to be battery powered. So they have these massive battery packs that will allow you to collect all the data you need. Shielded rooms also help. You can build a Faraday cage. They're not that difficult to make. You can literally create them out of chicken wire, but you need something that's large enough to house an entire subject and monitor and whatever. These are falling out of fashion nowadays. They're not that common, but obviously people still have them. And active electrodes and short wires can also help. So if you're getting that amplification right at the source of where the electrode tip is, there's a less likelihood of that 60 hertz noise infecting the signal. It's not impossible to completely eliminate it through active electrodes, but you can use a combination of active electrodes and like similar to what wearable sensing does, where they create a Faraday cage around the electrode itself. That can almost completely eliminate the 60 hertz noise. You guys are going to see this, but with the Cytons, we have an abundance of 60 hertz because the amplifiers themselves are not shielded. So most research grade amplifiers, they're sort of in these nice containers and boxes that will help. Typically, they have some plating in them that will keep out some of that 60 hertz noise, but we just have a bare circuit board. It's in 3D printed plastic, but that's not going to do much. And then skin potential changes. Sweat is one of the biggest ones. You can usually mitigate this by having a cold room and caps that are made out of breathable material. That's why we usually use this lycra or sports fabric material and not like, I don't know, nylon or not. Well, nylon's okay, but not, what is this, like ABS or whatever. Um, but having the rooms be cold also helps to just not sweat. Uh, Although then you can run into participants shivering, which can cause additional cold artifacts. Usually 68 degrees is sort of the sweet spot that we try to. I have no idea what temperature it is in here, but it's not too warm, so hopefully we're not getting that many sweat artifacts. It's usually not as much of a problem because the variations tend to be random. So remember yesterday I was talking about systematic artifacts and how those are an existential threat to your findings if you're not correcting for them. Your skin potentials, unless you're doing a fear experiment or something, which your galvanic skin response is a known factor, your your sweat on your head is probably going to be oscillating very slowly at the same rate throughout the experiment. And as long as you didn't design your experiment such that you're getting like a set of trials on the downturn and a set of trials on the upturn, which would be very difficult to plan, it's probably not going to be a huge problem. But you can also just deal with it by applying a really, really low high pass filter, usually 0.01 hertz or 0.1 hertz, will completely eliminate this drift. It can be an issue if you're doing single trial analyses. or if you're looking at low and slow oscillations. But for ERP research, it doesn't, like averaged ERP research, it doesn't tend to be that much of a problem. And again, you can remove it with a 0.1 high pass filter. So that's it for lectures today. And now we'll move on to actually setting you guys up with the open VCIs. But before we do that, does anybody have any questions?